All right, and we're now going to look at a central force that is common to what we've been doing. We've talked about it on and off. We've used results from it, but we'll talk about it in its full detail. And that's the concept of gravity. Now, Newton, during a plague, was quarantined to his farm. He saw an apple fall. And while he saw the apple fall, little red apple falling from a tree in the orchard, and it's falling down. But in the background is one of those afternoons he saw the moon in the sky. And the ancients knew the moon moved, and he was thinking of the motion of the moon and the motion of the apple, and wondering if the moon was falling towards Earth. It just missed. And it was in some form of uniform circular motion. And if it was in some form of uniform circular motion, if it was falling towards the Earth and missing, then there would be some force pointing inwards between the moon and the Earth. Let me call the Earth here. And this is what started him to develop calculus and the physics that we know as Newtonian physics. The thing about revolution, the moon's in that direction. The thing about Newton's third law coming into play here, in Newton's laws, is once he solved these, it wasn't hard for him to figure out that the moon, the force between the two bodies would be proportional to the mass of the Earth and the mass of the moon divided by the distance squared. And the reason the distance between the two squared is important is if we think of this as a source of gravity, as you get further away, in all directions, that source influence gets smaller by an expanding beach ball. Right? You can think of like there's a ball around the Earth, and the force of gravity is spread out amongst the outside of it. And as you get further away, that ball covering everything gets larger and larger and larger. And so you have to take the total, whatever's causing the force, and divide it by the surface area of that big beach ball. And that's why a lot of things that have a point source, like light, like electromagnetic charge, like gravity, as they spread out, the geometry of the situation is going to divide them by r squared. Because the surface area of the bigger and bigger sphere goes up by r squared. Right? The equation for surface area is 4 pi r squared. And so as your sphere gets bigger, it spreads out whatever's causing the force by r squared. And so we're looking at the cause divided by how far it's spread out. You have to wonder, well, what happens to the 4 pi? And I do make a warning, 4 pi's pop up a lot in the type of geometry we see from these type of physics. Well, this is proportional, and there's a constant of proportionality. And Newton said, well, it's not just the Earth and Moon doing it, it would be any two objects. And so the force that the Moon feels due to the Earth is the mass of the Moon times the mass of the Earth, get my r squared in here, divided by the distance between the two squared. The force the Earth feels is the equal force, but in the opposite direction. So the Moon feels, F of Moon is in this direction, and the force that the Earth feels is in this direction. And so this was Newton's big idea, that there was a central force that caused this rotational motion, and he called universal gravitation, and this is the universal gravitational constant. And the universal gravitational constant actually took ages to find out. Cavendish finally worked it out with a really nice experiment, but I'll give it to you here. It's 6.674. So G, I'll write it over here. 6.674 times 10 to the negative 11th Newton meters per, what are my units here? Newton meters squared per kilogram squared. And that's the gravitational constant. And so the kilogram squared cancels the kilograms here, the meter squared cancels the meter squared here, and you're just left with force in newtons. And so that's the gravitational constant. Now Newton then worked with this for extended bodies of objects, and he was able to go back and revisit Kepler's laws. A nice thing that pops up in this a lot is that inertia comes into play with objects that are under the influence of this type of gravity. So if I'm at the moon and I want to find this force on the moon, and I actually want to talk about the motion of the moon. So we're going to say this is the force causing the moon to move. But the moon's inertia, ma, right? Well, that's also equal to the force. And so I can set these two things equal, and figure out what the acceleration that the moon is going to experience is. That's the mass of the moon. But notice what ends up happening. The acceleration the moon experiences is g times the mass of the Earth divided by r squared. And this is the potential field, and this acceleration is very similar to g. And the only thing that matters to it is the mass of the Earth. And so it's the interplay between the inertia of the moon and the gravitational force the moon is experiencing. Newton never could figure out why gravity was equal to inertia. And that this mass was the same as this mass. And it's one of the unanswered questions in physics. Gravity and inertia are two separate concepts. They depend on the same quantity. How these quantities are linked, we don't know. How inertial mass and gravitational mass end up being the same thing. Well, one other thing, and your book does this nicely, is if I look at a body falling near the Earth, it's experiencing inertia of mg, which is the same as the gravity of the mass of that body times Earth. And then the r we're going to use is the radius of the Earth. Look at the radius of the Earth, because we're near the surface of the Earth. And so with this, we can cancel these out, and we can use this to find the mass of the Earth. And this was called weighing the Earth. It was a project that was undertaken. A lot of surveyors did this. It was experiments to find out what the mass of the Earth was, because we wanted to make sure we were getting g correctly. And so a lot of experiments went into finding g in the late 1700s and early 1800s. And with English colonial expansion, because they were surveying, they were really wanted to find the radius of the Earth and some of the effects of mass. Some notable examples of things they found. They found a plumb bob that's supposed to point to the radius of the Earth, actually points a little bit off due to the distribution of mass in the Earth. And they noticed this when they were in India, and the Himalayan mountains were causing the plumb bobs to deviate a little bit more because of the gravitational influence on it. And so they really, really wanted to calculate the true mass of the Earth. And this is the mathematical simplicity that Newton gave us here, was we know this from Galileo. We know the inertia from Newton, and we know the acceleration from Galileo, and if the Earth is doing this, then in knowing this acceleration, we can figure these things out about the Earth. And we've had that since Eratosthenes, and so this was the next game, was finding these two things. And there's some interesting experiments in it. But so here we have a central force that causes bodies to move. And in the next little bit, we look historically at a simpler way of doing this. Kepler had figured out what was happening with the sun and the planets, and he basically figured out the calculus that makes an ellipse come across. And so what Kepler said was that all planets move in an ellipse around the sun. I'm gonna accent the ellipse, and so there's a major axis, semi-major axis, and a minor axis. And then there are two foci. Get my axes back here. And there are two foci. And the idea is I can physically make a ellipse. If I take two pins and I put a piece of thread around them, and I stretch the pen out with a pencil, the thread will make a triangle between the ellipse. And this length 1 and length 2, will change as I move across, but the sum will always be the same. Some constant. I'll just call it big L. And so as I move this, I get new triangles that add up L1 and L2. And that's the geometry of an ellipse. Newton looked at the geometry and the calculus with it and was able to take Kepler's laws and turn it into what we have. But Kepler's first law is, whoops, controls. Let me see if I get my brush. There we go. First law is all planets move in an ellipse with the sun as one focus. Now you'll hear me say a lot of times that we can approximate Earth's orbit as a circle, not an ellipse. It is an ellipse, but it has it is very, very circular. In fact, if we were to draw the sun, and then in the second point of the ellipse, it's within inside the sun, and so we're very close to being circular in our orbit. Not all the planets' orbits are like that, but that's the first of Kepler's laws, and he used this using Tycho Brahe's data. And the second law was that if I look at an imaginary line drawn from the sun to the planet, and it moves from here to here, the area that it sweeps out, area 1, area 2, is the same for the same given amount of times. So if T1 moves area 1, then T2 moves area 2, but area 1 is equal to area 2. Okay? And that's the second law, that planets sweep out the same amount of area in their orbits. And this is the part that Newton really was figuring out, because the calculus of this motion does generate area sweeping rules. I think it's one of the joys in the calculus side of this. And so what he was able to do was to take the radius, or the length, of their average distance, and he was able to state that the time, the period, so the period of motion squared is equal to their average distance cubed. And that we'll find is easily observable. And so any two planets do this. So we'll say Earth, make a radius look like the Earth, And so we can do the radius to Jupiter, and to Earth. And so they make these perfect ratios. And that's what he was observing. He was observing the effects of different planets and the periods that they shared with each other and their distance away. And what's neat is we can get this, and Newton did this rather nicely. And that's what I want to do here. And your book does a good job with this. So what we're going to say is that we're going to take a planet, and we're going to say that it has some force on it. That is equal to G the mass of the planet times the mass of the sun. I'm going to make the mass of the sun big. And R is going to be the distance between them. But this is also equal to the mass of the planet times the acceleration the radial acceleration, or the mass of the planet times its velocity squared over its distance. Whoops, not squared now. So we can set these equal on the far ends, Newton's law and uniform circular motion, and the m's will cancel. And I can get rid of 1r here, canceling that. And so I get G, the mass of the sun divided by the distance, is equal to its velocity squared. But we know that velocity is 2 pi r times its period, right? If this is the time it takes to go once around the circle, and this is the distance to go once around the circle, distance over time is velocity. So G mr is going to equal 4 pi squared r squared over t squared, which we saw when we did the moon calculation. And let's do some cross multiplying. So I'm going to get Gm as some number. We don't know what Gm is. And I'm going to get t squared. And I'm going to divide this by 4 pi squared. Is r cubed. And right there is hiding Kepler's rules. And what was really neat is Kepler did it. He said, well, we'll let this be in years, and we'll let this be in the distance the Earth is from the sun. So that's called an AU. So if we measure this in AUs in astronomy, that's the only equation we need to do. If this is measured in years, and this is measured in AU. Newton's stuff over here becomes 1 in these units. And in the astronomy work I do, we measure things in years and AUs for this reason alone. The equation becomes this. We don't have to worry about all these extra numbers across. And this also gives us a hint at what these numbers mean when we change the units. And that's a task you might want to play with, is if you take G as being Newton's constant and m the mass of the Earth, and change it so that it's measured in years and distance from Earth from the sun, you'll find this all reduces down to 1. And so Kepler had this nice simple rule with 1 if we use the right units. And that's one of the arguments for choosing your units for your system. This equation is so much easier to deal with than remembering this tacked on bit. But it derives nicely from there. And it's a good argument for not using SI units only, but using units that work the best for what you're measuring. All right, I'll leave it at that, And that kind of wraps up all of chapter 6.